Alright, so after that first proof by induction that we did, and we proved that sum of n consecutive integers starting from 1 to n is n times n plus 1 over 2. Let's do another proof by induction, and this time what I'm going to do, I want to prove that the number of elements in the power set of another set is 2 to the n if n is the number of the original set. And I want to do this proof by induction. So effectively, this is this is what I have. Let's suppose that A is a set, and I call this set of members A sub I, such that I is from 1 to n. So effectively, this set is going to be a set of elements A sub 1, comma A sub 2, comma A sub 3, comma all the way to A sub n. So because of this, then I know that the size of A is equal to n. Basically, set A has n elements. Now, the power set of, if that was the case, then the size of the power set of A is going to be 2 to the n. Meaning that if my original set has n members, then its power set will have 2 to the n members. Where here I would say, and this is what I want to prove. I want to prove if size of a set is n, then the size of its power set is going to be 2 to the n. And remember, this means power set of A. So this is the theorem that I want to prove. Now let's just take a look at it on the side here and see if we could kind of give a couple of examples and see how it works. So let's say that set A, let's say that it is a set of two numbers, two elements, A and B. Then the power set of A will be a set of sets where each of the sets is a subset of the original set. So of course, empty set isn't a subset of any set. So the power set of a set contains empty set, then a set of one elements of A, and the set of both elements of A. Okay, so here if this set had size 2, then its power set will have size 4. Okay, let's take a look at another one. Let's say that B is the set of 3 elements, A and B and C. Then its power set of B again will have 5. Then each of the elements has one set. Then each pair of elements, A, B, AC, and BC, and of course the whole thing. So let's see how many there are. 1, 2, 3, 4, 5, 6, 7, and 8. So the power set will have 8 elements in it, which is 2 to the 3. So n is 3 here, and the power set will have the size of 8. So this is what I want to prove. I want to prove that if my original set has n elements, then its subset will have 2 to the n elements. I do this by proof by induction. So let's see how we do the proof by induction in this case. So the proof is by induction. Now remember, to prove by induction, I would have to do two things: base case or basis, and then the inductive step. So in the basis step, all I need to do is to show that this statement holds true for the base case. And the base case usually is the smallest element or smallest object that you're trying to prove this property on. Since I'm proving that my property on sets, my base case will be the smallest possible set that I can get my hands on. So you can start with base case empty set and also base case 1. For the base case empty set, the statement is obvious. If your original set is phi, which will have 0 members in it, its size is 0, then the power set of phi will be a set that's made of nothing, which is phi. And so basically it would be a set of phi. So it will have one element. Therefore, the size of the power set of phi, since it has one set, which is the empty set, will be 1, which is 2 to the 0. So that proves true. Sometimes you might want to. I want to show also this with the set that's made of one element, because that would be a little bit easier to see and nicer to see. So I say that if my base case was a set A, and I'll call this set A sub 1, that is only made of one element, okay, then its power set of A sub 1 is going to be made of empty set and the set itself. That's only one member. Therefore, the size of the power set A sub 1 is going to be 2, which is 2 to the 1, right? So here n is 1, and here I've got that. So if the size of A sub 1 was 1, then the size of its power set is 2. Okay, so my base case is shown now. So my base case, I just showed my base case here. So the base case is proven. My next challenge is to do the inductive step. So in the inductive step, here's what I'm going to do. So I've got inductive step. What I'm going to do is this. I first start with my hypothesis, and I assume the hypothesis is true. Then I show that by induction that one set more than what I suppose for my hypothesis, the statement holds true for it as well. So what I'm going to do in my hypothesis is that assume the statement is true. Assume that if the size of, here I call it A sub n minus 1, is n, where A sub n, so if the size of A sub n, a set, is n, where A sub n is made of elements A sub I, such that there are n of these i's, right? Then the size of the power set A sub n is equal to the size of the power set of it is equal to 2 to the n. So I assume this, right? I assume that this statement is true. Let me just draw a line to it. Assume that is true. Then what I will do is that I want to show that if that were the case, show that size of a sub n plus 1, if the size of a sub n plus 1 is n plus 1, then the size of its power set a sub n plus 1 is going to be 2 to the n plus 1. So assume that this is the case, that if you have a set with n members in it, then its power set has 2 to the n elements in it. Show that if you add one element to this set, then the power set size will grow by 2 to the n plus 1. Grow 2 to the n plus 1. So this is what I want to show. I want to suppose that if I had a set with n elements, suppose that or assume that its power set has 2 to the n elements, then I would prove that if I add one element to this, I double the size of its power set. So I want to show this. Now let's see how I'm going to go about doing this. So I start with my assumption. I say that my a sub n is effectively a set of a sub i's, where I is between 1 and n. Okay, so it's going to be something like this: a sub 1, a sub 2, a sub 3, all the way to the a sub n. From here, its power set, so the power set of a sub n is going to be the empty set, the set a sub 1, the set a sub 2, to the last element, a sub n. Then the set of each pair of these, so a sub 1, a sub 2, a sub 1, a sub 3, all the way to the set a sub n minus 1, a sub n. So these are the two set elements, then the 3 set elements, 4 set elements, 5 set elements, all the way to all of them. So a sub 1, a sub 2, a sub n. And we know that this has 2 to the n elements, okay? Because that's what we assumed. So our assumption is that then these guys are going to be 2 to the n of them. That's my assumption, right? I don't want to enumerate that. I just assume that this is true. Now I want to show that then if you add one element to this set, this size grows. Okay, so then let's do this. Then I create the a sub n plus 1 to be the union of a sub n and just one member set that's made of element a sub n plus 1. So I'm gonna build this set. So a sub n is gonna be, actually let me make it a little bit neater to see. So this element, then I'm going to create this new set that's made of a sub n union with the element a sub n plus 1, which basically then it will be this set. It will be a sub 1, a sub 2, a sub 3, all the way to a sub n and a sub n plus 1. Okay. Now let's take a look and see how its power set would look like. So the power set of this guy, so the power set of this a sub n plus 1 is effectively made of the power set of a sub n union with just one additional element, and I call this element a sub n plus 1. Okay, so what this means is that now in this guy, the power set here is going to be the power set of a sub 1, a sub 2, a sub n, a sub n plus 1. Right? So I already know what power set of A sub n is. It's basically all these guys, right? And so you see, when I'm adding each member of these elements or these subsets into my original subset, I start from an empty set, then I add one element to it, and then I go through all of the possible one element items. Then I add another element to them, and I go through all the possible two element items, and so on and so forth. So this subset, power set of the n+1 member, is effectively made of the original power set of A sub n, okay, plus all of these elements in the power set of A sub n added one element, the last element, to them. So then plus the power set of A sub n unioned with the additional element, right? So let's see how then this would look like. So so then the power set of the A n sub n+1 is going to be the empty set, so the set of the empty set, and one element items, A sub 2 all the way to A sub 1, A sub 2 to A sub n, right? So it's going to be all these 2 to the n plus the additional element added to all of these. So then it's going to be then A sub n+1, actually, comma, and then add A sub n+1 to this first element. So it's going to be A sub 1, comma, A sub n+1. And then added the last element added to this subset, which is going to be A sub 2, A sub n+1. See, I'm adding effectively to every single one of these guys just the last element. So which means that the last element of these is going to be A sub 1, A sub 2, A sub 3, all the way to A sub n, added to it A sub n+1. Right? So if these were 2 to the n, these guys are going to be also 2 to the n elements. From here then, the size of the power set of A n+1 is going to be these first 2 to the n's plus these 2 to the n's, okay, 2 to the n, right? So which effectively then, from here I know then that the power set of A n+1 will have the size of 2 times 2 to the n, which will be 2 to the n+1. Therefore, the size of the power set of A sub n+1 is going to be 2 to the n+1, right? And this will prove my my induction step, meaning that if the size of A n+1 is equal to n+1, then the size of its power set A n sub n+1 is going to be 2 to the n+1, and therefore my theorem is proven true, and this will conclude my proof by induction. So again, to recap what we did to do with the proof by induction, I showed my base case scenario that the statement is true for the smallest set. Then I assume that the statement is true for a set made of n elements. I showed that it will be true for a set with n+1 elements, but basically adding one element to it. And after this final step, I completely proved my theorem. here. Okay, the next proof by induction I want to show you is another algebraic proof, and it basically calculates the principal amount of a loan payment based on the interest rate and the payment rates that will be applied to the original principal amount. So on page 24 of the COSC book, there's a description about how this calculation is set up and where the equation comes from, and then we will try to prove the equation. So first, let's set up some names for our variables that we will be working with. So let's say that P to be the principal amount. So if you go and get a loan from the bank for P dollars, that would be the value. Let's suppose that I is your annual interest rate. That you will, the bank will offer you, for example, 6%. That would mean that you will have 6% effectively added to the amount of principal every year. But since most of the time you pay monthly, we would basically calculate that to be as the amount Y to be your monthly interest. Okay. And sorry, M will be this amount, just to keep with your with the definitions that is on the COSC book. So we say that M to be your monthly interest. And then also we assume that you pay a Y amount of dollar every month. So this will be your monthly payment. Okay. So we've got the principal. That's the amount that you take out. M to be the monthly interest, and P to be the monthly, and Y to be your monthly payment. Now, two things happen every month that you pay. Every month that you pay, first off, the amount that you took out, it effectively accrues some monthly interest. So that monthly interest will be added to it, and then from that amount, then the monthly payment that you pay is going to be subtracted from. So every month, if your payment is more than the monthly interest addition to your original payment, your original loan tend to decrease over time every month you pay. Now, if your monthly payments is less than the amount that the monthly interest adds to your principal, your loan will grow. So now we want to show that after T months. So if T is basically after T months, then you owe P sub T to the bank, and that is calculated according to this equation: P, original amount, multiplied by M raised to the T, number of months, the monthly interest that you accrued, and then from that, Y, your monthly payment, times this amount is subtracted, M to the T minus 1 over M minus 1. So we want to prove this. We want to prove that if you had taken out P amount, the amount, equivalent dollar amount of P from the bank, and you agreed to pay M dollars every month with a monthly adjusted interest rate of Y percent, then you will then after T months you will owe this much money to the bank, and so you're paid off when this money becomes zero or effectively negative. So we want to prove this by induction. So what I'm attempting to prove is this equation. So again, if you remember, for proof by induction we have to prove two cases. One, the basis case, and two, the inductive phase or the induction step. Okay, I need to prove both of these two cases to be able to show and prove this true. So first, let's take a look at our basis case. The basis case, again, as I said, is going to basically be the minimum or the smallest number, the smallest amount, the smallest statement that this equation talks about. So the smallest is when you're in your 0th month, before you make any payments. You want to show that this equation is true. So we know that before we make any payments at month 0, we owe how much to the bank? P, the same amount that we took out. So if T is equal to 0, then according to this equation, P sub 0 is going to be equal to P times M to the 0 minus Y times M to the 0 minus 1 over M minus 1. We know that raising any number by 0 is equal to 1. So then effectively this becomes 1 and this becomes 1. So then it's going to be P times 1 minus Y times 1 minus 1 over M minus 1. So this is 0 then. Then this will be equal to P times 1, which is equal to P. So according to this, your P sub 0 is equal to P, which is the case. So basis case is true. Okay, so we knock down then the basis case. So we're good here. Now we've got to go and show our induction phase or the induction step. So step number 2 is my induction step. And usually the induction step or the inductive step is the one that takes some work. So in the induction step I have two things. Assume that it's true for T, then show it will be true for T plus 1. If I'm successful with doing that, then I'm good. Just to make this calculation a little bit more fun to play with and to work with, is that I assume, I'm just making a couple of variable name changes. So I assume that this is true, that this is true for T equal K. For some positive K. I already showed it for 0, so that's not going to help me. So I'm going to show that it is true for some positive K. So where basically K is positive. then I want to show that or prove that the statement is true for T equal K plus 1. Okay, so this phase, what I want to show or assume that P sub T is equal to P M to the T minus Y times M to the T minus 1 over M minus 1. So I assume this. then what I want to show is that, which I don't know it is, right? So this is what I want to show, that is p sub t plus 1 equal to p m to the t plus 1 minus y times m to the t plus 1 minus 1 over m minus 1. Is this true? Right? This is what I want to prove. This is my induction step. So in the induction step, I suppose that it's true for, sorry, as I said, for k and k minus 1. Let me just make some adjustments here. So there, and there. Yeah. You may start laughing at me because I can't even remember that I made my variable changes. So I want to show, is it true that if it's true for p sub k that, then is it true for k plus 1? Okay, this is my job. This is what I want to, what I would have to show. So let's start. So to start, I start with p sub k plus 1. How much is p sub k plus 1? P sub k plus 1 is the amount that I owe to the bank at month k plus 1, which means that if I have already paid up to month k, I had owed p sub k to the bank. Now in the past month, m will be added to it, which is my monthly interest additions, and then I'm paying y dollars, so y will be subtracted from it. So p sub k plus 1, which is the amount I owe on month k plus 1, is going to be equal to p sub k, which is the amount I owed last month, right? Because last month was my p sub k, multiplied by m, which is my monthly interest, and then from this amount I'm going to pay y, which is my payment. Okay, so p sub k plus 1, the amount that I owe on month k sub k plus 1, is p sub k, the amount I owed last month after I paid that month's payment, multiplied by m, which is the amount that's added to my account every month, minus y, the amount that I'm going to pay right now. So that's my p sub k plus 1. So we know that. Then let me just rewrite this here then. So p sub k plus 1 is going to be equal to p sub k times m minus y. Okay, awesome. So now I established how much I owe in the month p sub k plus 1. Now from my induction hypothesis, I assume that this is true, that p sub k is this much. So I'm going to basically replace p sub k. So replace p sub k with the amount that I assumed to be true. So p sub k plus 1 will be equal to p sub k, which according to my induction hypothesis is p times m to the k minus y times m to the k minus 1 over m minus 1. I haven't really done anything crazy yet. So basically I just replaced p sub k with its value, which basically comes from up here, right? This value. Basically replaced there. And remember, I still have to subtract y from it. Okay? So from here, let's go back all the way to the beginning here. So let's go way back to a cleaner sheet. So then p sub k plus 1 is equal to p times m to the k minus y times m to the k minus 1 over m minus 1 minus y. Oh, you know what? I forgot to multiply this guy by m. This guy is times m minus y. Okay. That was what I was missing. I was wondering there was some huge chunk missing here. It's because when I substituted p sub k, I forgot to multiply it by m. So the whole thing is multiplied by m, right? Minus 1 then. Awesome. This looks much more like it. Yeah, so p sub k plus 1 is equal to p sub k times m minus y, which is going to be p sub k mk minus blah 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 times m minus y, which would be my monthly payment. Awesome. This looks much better. So then now let's do this. Let's multiply m by these guys. So if I multiply m is going to be multiplied by this first element, and m is going to be multiplied by this second element. So this is going to be p m to the k times m minus y times m to the k minus 1 over m minus 1 times m, and then minus y. Okay, so this is good. So what I did is I haven't done anything crazy yet, so I just multiplied m by both of these elements. So it's going to be p to the k times m. Sorry, p times m, p m to the k times m minus y times that chunk times m minus 1 minus y. So then this guy is going to be p times m to the k plus 1. I hope everybody agrees with this. So then this is going to be p times m to the k plus 1. Okay. Minus y times, now let's multiply m here as well. So this is going to be m to the k plus 1 minus m over m minus 1, and then minus y. So again, what I did here, the second step, I did the same thing. Multiply m, and just clean up a little bit. So multiply your m by m to the k and m by 1. So you're going to get m to the k plus 1 minus m. Basic algebra. Awesome. Then let's factor out y. So then this is going to be equal to p times m to the k plus 1 minus, I'm going to factor y out. So it's going to be y times this whole thing, which is going to be m to the k plus 1 minus m over m minus 1 minus 1, right? So when I factor y out, then it's going to be y times this guy minus 1, and that's nice to see. Then what I'm going to do is that I'm going to do, so I just carry down the m to the k plus 1 minus y times, and then do the common denominator, m minus 1, keep the first numerator, k plus 1 minus m minus m minus 1. Again, I made another mistake. So this is going to be plus, and this is going to be plus. There you go. Much more like it. So when I take minus y out, I factor minus y out, then it's going to be mk plus 1 minus m over m minus 1 plus 1 and plus 1 over there. So then this is going to be p times m to the k plus 1 minus y times m to the k plus 1 minus m plus m minus 1 over m minus 1. So minus m and plus m cancel out each other. So then this is going to be, from here, p sub k plus 1 is equal to p m to the k plus 1 minus y times m to the k plus 1 plus 1. If only I could write neatly. So m to the k plus 1 minus 1 over m minus 1. And this will basically prove my theorem, because now I started from p to the k plus 1, and I worked my way down to show that p to the k plus 1 is exactly equal to p times m to the k plus 1 minus y times m to the k plus 1 minus 1 over m minus 1, which is what I wanted to prove. So my basis case is true, and I showed it up here, and my hypothesis case is true. My inductive case is true, which I showed it there, and both. So this proves 1, this proves 2, and 1 and 2 prove my theorem. And this is proved by induction. All right, so now that we these two examples, these two proofs, the proof that the power set of a set with n element has 2 to the n elements in it by induction, and also the proof of the compound interest in the payments on a loan by induction. This concludes our second unit, which in itself concludes our coverage of the mathematical symbols, mathematical notations, and definitions, as well as a couple of ideas for proving theorems and mathematical statements, proof by induction, proof by counterexamples, or rather contradiction, and also proof by construction, which we will encounter in this class for the rest of the semester. This finishes up the second unit, as I said. Second unit actually has 3 videos in it. It's a playlist. So, and you just finished the 3 videos. And the coverage of Cypser's book is Unit 0, pages 17 to 28. I'm going to upload your assignments up. You're going to have a couple of weeks to work on the first homework assignment that is going to be covering some mathematical proofs and notations, and that assignment should be now up and available on the assignment page on the Blackboard. And I look forward to talk to you in our next unit, which will be finite automata and regular languages. Thank you so much for looking and watching these videos, and I'll catch up with you soon.